Hello, I'll be explaining the code that we have for our line follower bot. This is written in heptagon. Uh, so the main function essentially just creates a timer and it calls a line follower node, which returns velocity that we want our bot to follow, and a bunch of other things. Among them, I just want to note that I just want you to note that the velocity output coming off the line follower is actually a vector, and actuate function actually takes care of the hardware abstraction and remapping of the function as well as finding out the direction. The st function and the state out, which is coming out of the line follower, essentially provides state information that the line follower is in, and the st variable is an array of states. So it provides you a cascade of which state the robot is in. This variable is printed in the supervisor.ino file, and it is useful for debugging because basically it gives the entire tree. It gives you which state the robot is in the entire tree. Um, Moving forward, I'll just go inside the actuate function first and explain that. So the actuate function essentially calculates the direction from the raw velocity that has been given, and the raw motor saturation function essentially ensures that the velocity that we are using is saturated to a limit and does not go, let's say, beyond 100%. And the remap motor values function, which is what you can see above, sorry, here, is basically where we have modeled the dynamics of the motor itself. Since both the motors are unique, the sort of reaction that they have to different PWM signals is different, and hence providing the same PWM value may not give the exact same sort of velocity of the wheel. And we've modeled that by basically discretizing the entire domain and find and making it as a set of linearly continuous functions. And the data for that is provided above as constants, and that is what is being calculated here. So essentially, this function remaps the value that you give it in. Let's say in our case, we for the above calculations, we're going to use velocity range to be 0 to 1,000. So whatever velocity you're giving in 0 to 1,000, it maps it to what is actually realizable by the motor. Now that we know, once we have the velocity vector, how do we sort of actuate the motor? We'll go deeper into the actual logic of line follower. So the line follower node actually, the line follower node has an automaton where it goes under three different states: the white line following, black line following, and parking state. Again, similar to how the line follower node in itself was providing a state output, each of the states of the automaton themselves provide an output for what state the sub-automaton is in, and that is what we can see here as well. And the velocity calculations are actually done within that. So, under each of these states, what you can see is common is that there is a sense function and there is a control function and a compute function. Sense, control, compute, sense, control, and compute. So for different cases, we're going to show you what what these functions do. Now, something that I want to point out is how the bot sort of transitions between different states is we have a line detector a node which just takes in the raw value of the sensor data and the timer for that particular node, and it spits out what sort of line it expects the system to have. Now, depending on this, we actually switch between different states. And once we switch, let's say we start in white line following, then the sense function uses the raw data to sort of abstract the color of the line. So if I give it white or if I give it black, the output is such that the subsequent functions will not really matter a lot. So let's say even a black line will look like a white line and it will function as if it's doing a white line following. In any case, I'll go to the line color detector logic. So yeah, so what the line color detector does is Firstly, let's say we assume that the color of the line is white. Once it is white, we have a particular variable here called criteria, which checks what sort of uh, which checks the criteria for switching. So, yeah, so whatever raw data we have, that is first converted into binary black and white values using thresholding. So, let's say we assume that the line color is white. Depending on that, we find out where the line is. So let's say 11101 or let's say 11000 basically means that the line is seen at the left two sensors and not at the other sensors. So what we do is we start with an assumption that we are on a white line, and depending on that, we calculate what sort of line we are seeing. And depending on what data we are seeing, so after thresholding, if the criteria is true for switching, then the line color switches. Now, in the next iteration, instead of assuming that the color is just white, it assumes that the color is the same as it was in the previous iteration. And with that, it is able to sort of robustly detect the line color. Um, Once the line color is detected and the switching is done between different states of the line follower itself, we can now see what the sense, control, and compute functions actually do. So I'll just move to the sense function. Yes. So the sense function essentially first remaps the values so that whatever minimum and maximum values have been measured for that particular sensor is being mapped to a standard range. Once we have these values, these are made color agnostic, line color agnostic with the help of the correct color function, which essentially, let's say if it's black, it's the same, and white, then it's 1023 minus that value. And this time the thresholding is done depending on what the line color actually is. So in which state the line follower is actually, and depending on that, the thresholding is done. Once we have the sense function, we'll now go forward to the control function. So the control function, if you are in white line following, or if it sees white color, then these are the different states in which it goes. So let's say if it sees this, then it means it has to take a left turn. If it sees this, it has to take a right turn, and so on and so on. And the definition of each of these states has been mentioned above as constants. Similarly, in case of black, these are the states, and in case of um, uh, parking, these are the states that it can be. Again, each of these definitions have been mentioned way above what each of these states mean. So depending on the state, the control is passed on to the compute function. Now the compute function has an automaton in itself, which has different values such as starting, falling straight line, turning left, turning right, and so on. And essentially, some of these functions have an internal trigger as well. So let's say if you're turning left, then only after a certain time, you'll have to stay in that particular state for a certain time before you actually switch to something else. And you can only switch out of that state if you have an internal trigger or if, let's say, the line goes missing. So similarly, the logic has been implemented here and the switching is done with the help of the control that was being calculated in the previous function. Similarly, for black compute, most of the information is the exact same, other than a bit of slight tuning here and there for that particular arena. Coming to parking compute, again, it's similar to how it was there for the other two. Depending on the sys-state value that is calculated in the control function, the state of compute switches, and depending on that, the velocity is calculated either from PID, or it's a constant left turning value, or a straight moving value, or so on, or it's a null value. So this is the entire logic that we have for the line followers. Thank you.